Hello there. So in this lecture I will be introducing to you the main concepts regarding an optical microscope. So I will be discussing of the terminology here, the main parameters of interest when we are looking at microscopes and how they behave. And I will be introducing to you two different configurations of optical microscopes. So a simple one based on 2 lenses and a less simple one based on 3 lenses, a so-called infinity corrected microscope. And this is a more modern configuration of microscopes, but nevertheless, let's start with the simpler one because it's better to progress in small steps at a time. And I will be introducing also the parameters that they help us to understand how the transverse magnification is being formed and how large field of view we can muster with optical microscopes so that how much we can see in just one go when we are looking at things using a bright field optical microscope. So this is what we will be doing here, and I think there's actually a lot of things to progress on this lecture, so please be patient with me on this one. So let's start by just general motivation on microscopes in general. And at the same time, when we are looking at it, we also learn better how a more complicated optical imaging instrumentation functions. And a microscope is a very good representative optical instrument where the main function of it is to image small things. So that this is basically the kind of main use of microscopes. As the name suggests, we want to see something, inspect something that are small. And when we are looking at how they function, of course, in a way we can understand microscope as just a more complicated and more powerful magnifying glass. And how much of magnification we can get if we are speaking of optical microscopes, then we get easily 10 to 2000 magnification. And if we put that into perspective, if we do not use a magnifying glass or a microscope, it's roughly a 1 millimeter sized objects that we can still see with our human eyes. And then if we can form a 2000-fold magnification, then that means that we are really able to see with an optical microscope something that is smaller than a micrometer in size. So that we can really actually see things that are quite small. So for example, if you think of a human hair, I think the radius of a human hair, of course, it varies on the individual, but is of the order of some tens of micrometers. So we can easily distinguish that kind of dimensions. And this is where the microscopes excel, and this is their main function. They are being used to image something that are small. And the conventional optical microscope that they can be used, they achieve around 200 nanometer resolution. This is maybe a good rule of thumb, a good number for you to memorize, that if you do not do any tricks, the diffraction of light limits the best capabilities to around 200 nanometers. Of course, there are so-called super resolution optical microscopes, and you can really do tricks with your, for example, fluorescent molecules, and you can achieve better resolution. You can also do so-called structured light illumination, and you can easily halve the achievable resolution so that you can really get around 100 nanometer of a resolution by just doing some tricks on your optical configuration. But nevertheless, there's always the kind of limitation due to the diffraction of light at some level. Where you could do better is that, of course, a optical microscope is not the only possibility. You can also have electron microscopes. And where they excel is that they can actually have a huge magnification. And I'm speaking here a million-fold magnification when you can use electrons to do microscopy. So this means in practice that you can quite easily achieve a kind of 0.3 nanometer resolution. And this is mind-bogglingly small so that you can really see things on a kind of atomic scale. The trouble what you have in an electron microscope that essentially you need to have your sample in a vacuum condition so that you don't have that much of capabilities of operating them on a kind of a normal air pressures. And then if you would want to, for example, image something that is alive, so for example cells and so forth, then electron microscopes are somewhat limited in their capabilities unless you go to highly sophisticated electron microscopy. So that is the kind of downside of electron microscopies. And this is one of the advantages of optical microscopes. And that's the kind of where they still excel. So that it's very easy to inspect living cells and living substances, living samples using optical microscopy. So that these are the kind of always there's some pros and cons with everything, every technology that mankind has developed, and so is the case with the microscopes. And these, of course, are just the kind of simple rules of thumb. If you would really start Googling around or using your favorite internet browser or ask an AI, then you would see that it's actually not this simple as I'm saying to here, but rather there's always a kind of changes into the things when you look more carefully of it. Now, let's start going into the actual business. So we can look into the kind of simplest possible microscope configuration we can think of, and that consists of two lenses as we were describing in the previous lecture. So we have the objective lens, that is the first lens that we have in our instrument, and then we have the eyepiece as shown in the figure. Both lenses, as we know in our previous lecture regarding several lenses, both of these lenses magnify the image of my object. But in practice, the eyepiece, the magnification of that is restricted to around 10 or 20x. So this is the kind of practical limitation. And what this then means is that the focal length of the objective FO will be around 1 millimeter. This is what the kind of implication is from there. So that then what we have is that we are then wanting to look how the objective lenses would be in practice to understand how we do microscopy. And there are several different kind of objectives and eyepieces in practice that will be needed when we are doing a kind of real inspection. And why this is so? Well, for example, if you want to inspect something, we need to start from a kind of larger field of view. You do not want to go right on to use the maximum transverse magnification, but rather you want to first see roughly how the sample looks like, and then only gradually you go into a higher and higher magnification to look into the kind of finer details of your specimen. And because of this kind of challenge or need you have for the microscope, then you will also have many kinds of different objective lenses. And then this is basically boiling from the fact that you need to inspect different kind of objects or the same object, but you want to inspect it with a different magnification. And subsequently, you have many objective lenses where the magnification is being changed, their overall field of view changes, so that how large of a field of view you can look at. And then also, if you can use your specimen that will be in an aqueous solution, then you will have a different objective lens. If you want to use oil immersion so that you get a better resolution, you can see finer details of your sample, then you have different objectives for them, and so forth. So it's actually a huge variety in objective lenses that you can buy. And then, of course, depending on the kind of overall quality that you need, you can buy cheaper ones, and then you can buy more expensive ones, especially, for example, in terms of the aberration corrections. So that they kind of, if you need to use spherical, not spherical, but the color aberration corrected objective lenses, then things become more pricey because you need to actually make an objective lens that is being formed by using several lenses. And for practical reasons, because you want to change these objectives on the fly when you are inspecting a given specimen, like the kind of relative distances that you have between the objective lenses in the frame of an optical microscope, they have become standardized. And this is the main thing that needs to be done in order for us to be able to change the objective lens and not touch the eyepiece as such, so that in a few seconds we can, for example, switch to a different objective lens that, for example, has a different transverse magnification, so that we can see either a fine detail of our specimen or the kind of whole specimen in one go. So basically, every objective, and this is how a two lens configuration works, every objective forms an image into the same image plane. And this is the kind of key here. And this gives us a possibility that we have a standardized distance xi. Xi, of course, is the distance from our focal plane into the image location, so xi can be standardized. So it is always the same distance no matter what is the actual objective. And this then gives us a possibility that we can always construct our microscope frames in mind that this xi will be only a given specific number. So, and this is being called a tube length L. And depending on the different vendor, different manufacturer of a microscope, it slightly varies. Some people use, or some companies use, a tube length of 160 millimeters, and the objective lenses have been designed accordingly with the eyepieces. And for some vendors, it's 200 millimeters. So that this is good to keep in mind, that if you need to buy an objective lens, please look what kind of objective lenses you already have, so that you don't accidentally buy a wrong one where the tube length is not the same, because then you start having a trouble. Of course, there are adapters, but nevertheless, my recommendation to you is that they just keep on buying products from the same company, unfortunately as it is. Now, let's look into the magnification that we can get. So basically, the transverse magnification is known that this is the minus xi per FO. So if you place in the barrel length, the tube length, then the transverse magnification of my objective lens is basically just the minus L divided by FO, where the FO is the focal length of my objective. And this transverse magnification is always marked into your objective lens. And this is what you know, that what is the magnification. Could be, for example, 5x, could be 20x, 40x, and so forth. And if you have, for example, a focal length of 32 millimeters objective lens, then the transverse magnification would be 5. And this is how things have been designed. And then is on top of that, you have the ocular, the eyepiece, and the transverse magnification of that is tenfold. Then the total magnification of my microscope turns out to be already 50, as we recall from the 101 on lens system. So that the total transverse magnification of two lenses is basically the product of the individual transverse magnifications of the lenses. So this is how things go. And we see that the magnification actually turns out to be quite large already with this kind of objective lens. Now, in addition to just looking at the magnification, NT, it's also important to kind of know how large of a field of view you can see through the microscope in one go. So basically how large images we can form. And here the parameter of interest is known as the field number, abbreviated as Fn on the objective, and this is essentially defined as the size of my intermediate image. And more precisely, this is the diameter of my intermediate image. So in the previous lecture, in the figure, basically the length of my intermediate image arrow, yi1 is related to this field number. So that's essentially the size of my intermediate image gives me the field number. And how that gives me the actual final field of view? Well, when we have both the transverse magnification, MT, and we have the field number, and we know them both, we can easily calculate the total field of view, FOV, of the objective lens, that it's simple as this, so that the field of view is the field number divided by the total transverse magnification. And this gives me a kind of understanding of how large of an image I can look at without moving the specimen in one go through the microscope. And needless to say, in a way, the larger the field of view it is, then the better it is for inspection, so that this in a way also is some kind of a parameter that depends on the objectives. So if you want to get a larger field of view, then you need to increase the field number, and then you usually need to also pay more for the objective lenses, because they will be larger objective lenses, and at some point you also start having compromises that you need to make. Incidentally, also how we see how the field of view is being changed when we are changing the transverse magnification, we see that if we go to higher and higher transverse magnification, the field of view actually gets smaller. So that now we start seeing that there's actually a compromise between how large of a field of view we can see in one go and what will be the subsequent transverse magnification. And we cannot get both at the same time because there's this inverse proportionality between these two variables. This is important to keep in mind. So if you want to see something in fine detail, you can do it, but then you're not going to be able to see the whole forest. You can only see the one tree, so to speak. Then let's now go into the other configuration as I promised. So the conventional 2-lens microscopes, they are being used, but the trouble is that they cannot be easily used together with more modern microscopy techniques. And I'm now more speaking about fluorescence microscopy, where in fact we are using fluorescent dyes as a kind of objects of interest. We tag our specimens, usually biological specimens, and we tag them properly with fluorescent dyes. And then through the microscope, we're actually seeing the emission of these fluorescent dyes. And then, depending on the type of the dye, the color might be different, so that you actually need to put some color filters into your microscope frame between the objective lens and the eyepiece. And this is the main challenge that arose when 2-lens microscope configurations were being used and developed further. And the solution here is that instead of using 2 lenses, we go into a 3-lens configuration, and this is known as the infinity corrected optical frame. And here the idea is that the objective lens now forms an image into infinity. And hence the name. This frame is known as the infinity corrected objectives and infinity corrected microscopes. And the configuration basically is being shown in the figure here. So now instead of the objective lens being forming an intermediate image somewhere here, it's not forming an intermediate image anywhere, but rather it's being forming an image at infinity. And then we add a 3rd lens here known as the tube lens that now is being forming an image at the intermediate plane. And after this, the eyepiece still functions as before, so that it's being taking this intermediate image, it forms an image into infinity, and then we have our eye in here to do the final inspection. And the infinity, we want to have the image at infinity so that the eye can work in a relaxed mode, because that's how the eye functions. It's easiest for the eye to look at far away distances for a long duration, so that otherwise the eye can get tired. And the fine thing here is that now we have a separation between the objective lens and the tube lens. Look at here, the rays are propagating along a bunch, that they are not being focusing anywhere, but rather they are being just propagating parallel to each other. This is the main thing to keep in mind. So the 3rd lens, known as the tube lens, now forms the intermediate image, like I said, into the focal plane of the eyepiece FE, and this ensures that then the eyepiece will be forming an image into infinity. The nice thing about this configuration, and this is the reason why this configuration has been developed, is that now you can actually add several optical components. Flat components, of course, are being needed, and we can add them between the objective and the objective lens and the tube lens, and this does not affect the image formation. So essentially, the nice thing here is that we can put color filters, we can put polarizers here, and we are not being changing the actual location where the image is being formed. We may slightly change for example, the kind of size, slightly, not really, but at least the location will be the same, and we do not need to adjust the eyepiece accordingly. And this is super nice, because then on the go, on the switch, we can just flip between different color filters, and then we can see the fluorescent emission from our specimen. And then when we are tagging different fluorescent dyes here, let's say some of them are emitting at the red light, I have a filter that only transmits red light. I can look how those dyes are being located, and then at the same time I have dyes here that will emit, for example, green light and blue light, and then with the filter I can control which emission I'm actually being looking at. And this is the thing that I actually need in a kind of more modern fluorescent microscope, so that I need to have different filters, and I need to have them here. I need to be switching them around so that I can change what I'm actually looking at the sample. I could also imagine of using a polarizing microscope, and then I would want to add a polarizer here and so forth. And the nice thing here is that I can add a piece of a glass, and because the rays of light are being propagating as a kind of a parallel rays, it doesn't really change the image formation as long as the components are flat with respect to their like outer rings. And the price we have to pay on these advantages, it is that now we really need to design the objective lenses that are specifically designed for this configuration. And that's why they are being called infinity corrected objectives. So please note the difference here compared to the two lens configuration. The objective lenses actually are now forming an image at infinity here. And subsequently, the kind of aberration control you need to do, aberration correction, then the problem will be different, so that you cannot just use a same kind of objective lens as in before in place and just put it into a different location, because then the kind of aberration correction does not work anymore as it was designed to work in the previous scenario. So please note that there is this challenge. But on the other hand, if you do not have a need to add components in here, you can still use, let's say, old-fashioned way of using two lens configuration, and then you can still use these cheaper objective lenses, and you can still do visual inspection of small objects. So that's not a like real problem in itself. The problem is only when you need a microscope configuration where you need to add components between the objective and the eyepiece. And that's when you start adding a tube lens and go into this infinity corrected microscope configuration. Now, let's still look into the other considerations regarding microscopes, and especially optical microscopes. Of course, in practice, the objects that we want to inspect, they are very close to the objective lens, and this makes it actually quite demanding to design and manufacture the objective lenses, because basically there will be large angles of incidence out of which the rays of light from the sample will hit the objective lens and propagate through. Subsequently, we will have plenty of chromatic aberrations and also other aberrations, and these need to be corrected. And there's no universally best objective lenses, so instead, when you want to do microscopy, you really need to choose what objectives to use depending on the application and depending on the actual inspection you want to make. So in practice, you need several objective lenses when you do microscopy. Different things that you should keep in mind, and this is just the kind of simplest possibilities that came to my mind. The thing is, the kind of actual problem is way more complicated than I'm highlighting here. Different possibilities that how your objective is actually performing image. The first possibility is that you have an object that is in air. That is a one way kind of like how you might want to do inspection. Another possibility is that the object will be placed under a so-called cover slip. And a cover slip is a standardized piece of glass where usually the thickness of the glass, the cover slip, is around 170 micrometers. So this is, for example, something that is often used when you have a kind of sliced samples of your biological substance. That you take a biological sample and you slice it into a kind of thin pieces, you put it between cover slips, and then you are imaging those. You're inspecting those kind of sample. When you are having an object in air, you could, for example, imagine that this would be a scenario when you want to inspect a human skin right on, and then you don't want to do any sample preparation. You rather want to just directly image the skin of your patient, and then basically you would have this configuration. The object would be in air. Then you have this possibility that you actually have a sample, you prepare it, and then it will be behind these cover slips. And this will affect the kind of scenario, how image will be formed. Then, like you have a possibility that the object is placed under a cover slip, but now between the cover slip and your objective lens, it's not air anymore, but rather it could be water, so that you change the refractive index profile, and subsequently the image formation will be changing. At least the aberration, like a correction, will be changing. And then you have yet again different possibility that the object is placed under a cover slip again, but now immersed in a microscope oil, where the refractive index is not close to 1.3 of water anymore, but rather the refractive index will be close to the refractive index of your cover slip. So you have different kind of scenarios already in place depending on the different kind of sample that you have. And this is actually a huge variety that you may have. So that depending on the kind of problem, depending on the application, you may want to use different kind of objectives. And why you need to use different kind of objectives is that the aberrations, the kind of aberration control, correction, you need the kind of specific conditions, and you need to take into account the specific conditions to do things properly. So for example, you have water immersion objectives. They are specifically designed to a scenario that you use them with water immersion. Then you have oil immersion objectives, and you cannot use them with water that much, so that you need to use microscope oils. And then you have also just air immersion objectives, so that you do not use water or microscope oil at all between the sample and your object, and so forth. So it's actually there's a plethora of different possibilities when you are performing imaging. Then the kind of thing that is related to the water and oil immersion objectives. Earlier we were describing the relative aperture, so that would be the f number of a lens, and that was being related to the kind of resolution of your lens, so how powerful of a lens you have. And now with objective lenses, this f number is not anymore a meaningful parameter to describe what kind of performance we can have for our lens. So essentially, what is the collection efficiency, and subsequently, what is the numerical aperture, what is the resolution of my objective lens. And instead of relative number, f number, we speak of a numerical aperture, NA. And this numerical aperture is being defined that the NA is the NI. This is the refractive index of the medium between the sample and my objective lens times sine of theta max. And theta max is the maximum angle out of which I can still collect the rays of light propagating from my sample into the objective lens. So basically, this is a way how do we design a numerical aperture. We have the refractive index profile of my medium through which the rays propagate from the sample into my objective lens, and then I have the maximum angle out of which I can still collect rays that then ultimately are forming the intermediate image and play a role in the image process. And based on this, I can define a numerical aperture. And the higher the numerical aperture is, the smaller objects I can resolve. So basically the resolution gets better. I can see finer details. And as we can see here, if we change the refractive index of my medium between the lens and the sample, I can increase the numerical aperture quite easily. And that motivates quickly for us to not use air immersion if you want to get the highest resolution, highest numerical aperture, but rather water immersion or oil immersion. So this is the kind of like nice equation to also see why on earth we want to go into these water and oil immersion objectives. Commonly, we either have air immersion, aqueous solutions, or microscope oils being used, but I must speak to you also that you could have a higher refractive index materials, and they could also be utilized. Especially I'm thinking of so-called solid immersion lenses, so that you would really, instead of having a liquid here, you would have a solid piece of a material. And a kind of a practical example out of this scenario that comes to mind would be semiconductor industry, where you want to inspect your semiconductor circuits. And most of the circuits, they are being done using silicon. Silicon, as we know all, it's a semiconductor. Therefore, it has a refractive index that is quite high. At the optical wavelengths, the refractive index of a silicon can be said to be around 3.5. So in that respect, it's a typical semiconductor. So that the refractive index of your sample is around 3.5. Then it also makes sense that you use solid immersion lenses, and then the surrounding medium will also be silicon, so that there you can actually have utilize the refractive index, the very high refractive index of your semiconductor, and then you can get subsequently a lot higher resolution. So you can see it yourself, what would be the resolution if you would plug in here, not 1.5, but rather 3.5, and you can instantly see that with a solid immersion microscope, I can actually see very fine details. And this is quite nice, especially when we are thinking of the modern semiconductor industry, where the components are actually super tiny nowadays. And this is one application where solid immersion lenses are being utilized. And those you can also buy from the market if you can take use of them in your imaging application and problem. But nevertheless, what we have here is that the numerical aperture, it defines the diffraction limited resolution. So it's a very important parameter to keep in mind when we are performing microscopy and we are thinking of the objectives that we have. And like I said here, it's important to keep in mind that it's not just a matter of your microscope, how the lens behaves, but it's also the matter of, can you put your sample in a different environment? So can your sample also be happy, live, and can you inspect it when it would not be in air, but rather, for example, in water, in oil, or even inside silicon? So these are the kind of some things that you should consider when you're imaging things. And please remember, ultimately, what limits, it's the diffraction of light that limits the resolution, unless you go the so-called diffraction unlimited optical microscopy techniques. But of course, those are beyond our course scope here. So I thank you for lending me 30 minutes of your precious time. I hope you learned a lot of microscopes. They are really cool instrumentation, I think. And please join me shortly in our last lecture, where we will be unraveling how telescopes behave. So thank you for your time and patience, and enjoy the day. Bye.